Hello, my name is Brant Robertson, and I'm a professor of astronomy and astrophysics at the University of California, Santa Cruz. I'll be speaking about Morpheus-Ice, a deep learning framework that enables the pixel-level classification of imaging data from astrophysics to Earth science. The main application I'll be describing is the use of Morpheus for the automated identification at the pixel level of the presence of ice in surface imaging of Earth by the MPP satellite. This work is done in collaboration with my computer science PhD student Ryan Hausen, along with members of the UCSC Ocean Sciences, Earth and Planetary Science, and Astronomy and Astrophysics departments. This work is done by the UCSC Computational Astrophysics Research Group. UCSC Comp Astro leverages the world's fastest supercomputers to model the physics of the universe and understand astronomical data using machine learning techniques. If you are interested in these topics, please feel free to contact me via email at brant@ucsc.edu. We'll begin by describing the original motivation of our deep learning framework Morpheus, and then describe how we've applied Morpheus to Earth satellite imagery. This image of Hubble Space Telescope data shows that astronomical images are richly complex. There are a huge number of objects with a wide range of morphological properties. We would like to understand and catalog the objects in these images, and deep learning provides an excellent opportunity to train artificial intelligence models to help in those tasks. Important tasks in astronomical image analysis include acquiring and processing the images, identifying the locations of objects and pixels associated with those objects, called source segmentation, and the classification of those objects that enable us to understand their properties and evolution. Machine learning has been used to conduct these tasks separately, usually on small cutouts of images that have been pre-processed as PNG or JPEG image files that abstract the pixel values from the detailed flux measurements of the telescope. We can use advances in computer vision for autonomous vehicles to perform segmentation and classification simultaneously on astronomical images. Autonomous vehicles must be able to identify signs, streets, obstacles, and people quickly, and localize those objects and people spatially. We can use semantic segmentation to perform object identification, localization, and classification in astronomical images and in satellite imagery. In 2020, Ryan Hausen and I published a new deep learning framework called Morpheus that provides pixel-level semantic segmentation and classification for astronomical data sets. Starting with Hubble Space Telescope data as seen on the left, Morpheus identifies which pixels contain sources and which belong to the background sky, seen in the center. As shown in the right panel, for every source pixel, Morpheus provides a classification into categories of interest. For astronomical objects, these classes include disk galaxies, photoidal galaxies, irregular galaxies, and stars. In detail, Morpheus scans through the image, classifying regions of the image pixel by pixel. By scanning through the image, each pixel is classified many times. This enables Morpheus to characterize its classification certainty for every pixel, and based on the distribution of pixel classifications, each pixel, and in aggregate each object, can be robustly classified. Morpheus was published in the Astrophysical Journal and selected as a research highlight by the journal Nature. Morpheus provides pixel-level classification at an accuracy comparable to object-level classification of previous methods. For more information, please visit the Morpheus GitHub project at morpheus-project.github.io/Morpheus. You can also pip install Morpheus Astro and visit our website for links to Google Colab and Docker images. Before describing how we apply Morpheus to satellite images of Earth, let's provide a detailed overview of the Morpheus model architecture, which is colloquially called a UNet. Morpheus begins by ingesting science-quality processed data files directly from the telescope or satellite. Any number of images representing astronomical passbands or satellite receivers can be used. Morpheus then applies convolutions to the input images, where the convolution kernels are learned parameters of the model that are optimized during training. The convolutions produce feature maps, which are convolved versions of the input images. The convolutions are padded such that the feature maps are the same dimensions as the input images, with one feature map for each convolutional layer. The feature maps are then downsampled via a pooling operation to provide lower resolution feature maps with smaller image dimensions. This process of convolution and downsampling is repeated several times, successively abstracting the input data into a latent space of much lower dimension. After several repetitions, the latent variable data is then supplied to a convolutional layer that preserves its size. The resulting feature maps from these convolutions are then upscaled using simple interpolation to provide the pixel values at intermediate locations. A residual link then concatenates feature maps from the upper arm of the U-net, matching feature maps with the same image dimension as the lower arm of the U-net. These feature maps are then provided to convolutional layers and upscaled, repeating the process with the concatenation of the residual linked feature maps until the output feature maps are the same size as the original input data from the observatory. Once the feature maps are the same size as the input data, the feature maps are processed through one last set of convolutional layers. Here, the number of convolutional layers reflects the number of output classes desired by the model. The output classifications from these final convolutional layers then provide the pixel-level classification images. Morpheus is then trained so that the properties of the convolutional layers produce output classification images that reproduce known classifications in the training data. This provides our final, trained, pixel-level classifications. Here we see an example of the output data from Morpheus for a region of the Hubble Ultra-Deep Field. You can see that Morpheus reproduces our intuition about which objects are disks, ellipticals, irregulars, and stars. Morpheus also produces information about when it's uncertain, as transition regions between clear classifications are marked as indeterminate. Morpheus has been parallelized to enable the pixel-level classification of enormous images. Here we show that Morpheus has classified every pixel of the major Hubble Space Telescope extragalactic surveys, such as the famous Candle survey. Morpheus will be applied to data from James Webb Space Telescope and Nancy Grace Roman Space Telescope when those future facilities take observations. Since Morpheus works on images of any kind that have available classifications for training, we can apply Morpheus to Earth satellite imagery. In this application, we apply Morpheus to classify features in the Suomi National Polar Orbiting Partnership satellite. Suomi MPP includes the Visible Infrared Imaging Radiometer Suite, VIIRS for short, that provides 375-meter resolution images of Earth at 6 minutes cadence, surveying the whole Earth every few days. Data for VIIRS is publicly available through the NASA Data Archives, allowing for open analysis of the datasets. Suomi MPP provides beautiful images of the Earth that clearly show familiar features such as land, water, clouds, and in polar regions, ice. On the left, you see a false color image using 600 to 1600 nanometer data to show a portion of the 36 million pixel images that VIIRS captures at a single time. In the center, you see a Level 2 data product, VNP29, available from NASA that labels land, water, clouds, sea ice, night, and bad pixels using the reflectance data from VIIRS. Given these data and labels, can we train Morpheus to perform classification of these images? How well does Morpheus do? Here on the right panel, we show the results of training Morpheus to reproduce the pixel-level labels provided by the Level 2 VIIRS data products. Morpheus achieves about 90% accuracy at the pixel level in classifying pixels containing ice. This provides a powerful new technique for the automated monitoring of ice coverage on Earth from satellite imagery. One augmentation that was required to apply Morpheus to the enormous Earth satellite data volume was an increase in the efficiency of the model. Using a technique called attention, which helps the model identify which pixels matter most for determining the output classification of an image, Morpheus can be refactored to classify much larger images at a time. This technique has enabled 100 times speedup of Morpheus, allowing for the pixel-level classification of enormous images. We have now applied Morpheus to an entire month of data covering the Hudson Bay and southern Arctic Ocean in July of 2020. This time was chosen to track the thawing of the Arctic sea ice in the bay, providing a time-dependent coverage of ice with time. Morpheus demonstrates remarkable performance, correctly classifying sea ice pixels at about 90% accuracy. Given that no substantial changes to the original architecture were required to reach this performance, it demonstrates an amazing flexibility of Morpheus to tackle problems throughout astrophysics and earth science. Thanks very much for listening about our work in applying the Morpheus deep learning framework to earth science images. We can now use Morpheus with the Suomi MPP VIRS data, or on data from other satellite images, to identify features of interest, and in the case of earth science data, track those features with time. Morpheus represents an important cross-divisional application of AI/ML developed by NASA researchers, where astrophysics models can be directly applied to earth science data. Thank you for your time.